So this is the again magnitude of the transfer function, 1 over square root of 1 plus omega or omega c whole squared. So that means this is the, if omega is the input frequency, then you're looking at the magnitude of the output divided by the magnitude of the input, right? So now when you're looking at decibels, because this is the ratio of voltages, you do 20 log to the base 10. That's the decibels, right? If you have power, you just do 10 log 10, 10 times log to the base 10 for decibels. Okay, so you do 20 times log to the base 10 VO of j omega divided by VI of j omega, right? That's how you get decibels. So you do the same thing on the right hand side, 1 over square root 1 plus omega over omega c whole squared, right? So now omega c is the cutoff frequency, right? So if you notice, in our case it was about 160 hertz, and when omega is much greater than omega c, so if you remember, the way where we are measuring the slope was between 1k to 10k, which is much greater than 160 hertz, right? So that means omega or omega c whole squared would be much greater than 1. So I can write this approximately as 20 log to the base 10 1 over omega c, right? And which is a pretty good approximation, because omega or omega c whole squared would be much greater than 1. Everybody with me? Okay, so that means this is equal to negative 20 log to the base 10 omega plus 20 log to the base 10 omega c. With me? Right? So that's it. So when omega changes by 10, right, then log 10 of delta omega, let's say, okay, so this is, let's say, what do you want to call this ratio? Let's say R1. Okay, so let's say R1 is negative 20 log to the base 10 omega 1 plus 20 log to the base 10 omega c. R2, now I increase omega 1 by 10, right? So I went from 1 kilohertz to 10 kilohertz, right? So negative 20 log to the base 10 times omega 1 plus 20 log 10 omega c. Okay, so now, since I want to compute the slope, I'm asking how many decibels does your the response change if I change my frequency by 10 hertz, by 10 times, right, for decade. So that means I do R2 minus R1. This is delta y in decibels. This will be equal to, I subtract this from this, these guys cancel out, so it will be negative 20 log to the base 10 omega 1 over omega 1, right? So this will be equal to negative 20 log to the base 10. This will be equal to negative 20. So that's how you get negative 20 decibels per decade. Okay, so this is because we have omega in the bottom here, and that's why it's called the first order. If it's a second order, you'll have omega squared in the bottom, in which case you'll get 40 decibels per decade here, and so on. Okay, so what does that mean practically? That means this is the slope of the transition region, right? So that's how fast your response is going from high to low. That means first order response, it will cut off the high frequencies very slowly. If you want a very sharp response, then you want to build higher order filters. Okay, so the higher the order, the more fast the cutoff will be. But there are other complications you'll have, so there are other techniques to take care of those complications. So in practice, you'll hardly ever build a first order filter, because usually you will need much higher transition, right? So higher order filter design is a topic in itself. We may get to it a little bit in this course, if we go fast enough, but maybe not. But anyway, so that's where we will stop.